Okay, I think we're going to go ahead and get started with our first afternoon panel. We decided to combine, one of our speakers is not here, Omar Abdulaziz, and so we decided to combine the next couple of panels into one panel with 5 speakers. Andrew Williams is not here yet either, but we expect he will be here before he has a chance to, it's time for him to speak. Talking about methane emissions, how that relates to climate change. Obviously, we're sitting on top of the Marcellus Shale in this state. It's kind of taking the place. It's resulted in displacement of a lot of coal plants with cheap and plentiful natural gas. And natural gas is twice as clean as coal with respect to the carbon emissions when you generate electricity from it, but there are a lot of implications of methane leaks and methane emissions throughout the extraction, production, delivery process. So we want to have this panel that's really going to look at what are some of the impacts of methane emissions and what's the present danger, what's achievable, and then Professor Fershee and Andrew Williams are going to be talking more about the legal landscape associated with methane emissions. So we've got our first 3 speakers, a couple of them from Penn State University. We're going to start off with Kenneth Davis, and then Zach Barkley, and then followed by Derek Johnson from our own WVU. And then following that, the legal discussion will be with Professor Fershee and then Andrew Williams. So with that, let's start off with Kenneth Davis.
Thanks very much. Delighted to be here. Zach and I have a lot of graphics and numbers to show you, so fasten your seatbelts. It's going to get nerdy quick. But you wanted to hear this, so it's packed, so just a warning. Acknowledgements, Zach and I are presenting, but this is work of many, many, many people at Penn State and other institutions. And funding, since we care about politics here too, federal government funds a lot of what we do even now, and it's very important work to actually get at the scientific basis of some of these questions. Also have had some support for this work from the Environmental Defense Fund, and Andrew should be here later representing them. So, big picture. I'm going to go from the whole planet down to, and then Zach's going to get to West Virginia in particular. I'm the fun part. He thinks he's the fun part. So methane and global climate. How much has methane concentration changed, and how significant is this for the climate, just to start things off? Let's start with how much the concentration has changed. Here's the very, very long scale, 500,000 years, ice core data. So on this figure, this is the past going towards the present. Methane's up top, and you see it wiggling up and down with glacial interglacial cycles between 400 and about 700 or 800 parts per billion. And then something strange goes on very recently. So we'll zoom in on the very recently as being the last 10,000 years. That's not all that recently. But this is 10,000 years in the past to the present, methane around 700 ppb, and then suddenly something remarkable happens. This is the past 200-year view of that, and so you can see that industrial revolution has led to something remarkable. This is caused by people. We know that. There's no question at all. Not going to go into the background of that at the moment because time is limited. If we then zoom into that most recent time period, thanks to NOAA, Global Monitoring Division, Boulder, Colorado, they maintain these sorts of measurements for the planet. And you can see from 1980 to 2020, there's an increase and then a flattening, then an increase again. And unlike the previous figure where I said we know this is caused by humans, we don't really understand this. We don't know why these recent small fluctuations are happening because we don't know the methane budget of the planet that well. We have a lot of hypotheses, but we can't answer that question with confidence yet. Okay, so how significant is this for climate? So on this figure, if you looked at this axis, you saw methane in parts per billion. On this axis, you saw radiative forcing in watts per square meter. So let's take a look at methane compared to other greenhouse gases in terms of the radiative forcing. Radiative forcing is the impact adding this to the atmosphere would have on the radiation escaping from the top of the atmosphere before the Earth came to equilibrium. Yeah, whatever. So it... Pardon? Sound. Is that better? Okay, I'll head straight into I can hear me now. So this is radiative forcing of all these different anthropogenic drivers to climate from pre-industrial to present. And you'll see methane is a significant but far from dominant piece of the total forcing. The total is down here, a little more than 2 watts per square meter. This is only going up to 2011, but that's not too far in the past. Methane is maybe 20%, 25% of that. So the radiative forcing, again, if you add a greenhouse gas to the atmosphere, less infrared radiation can escape to space until the Earth warms up to retrieve the balance. And it is a calculation of, if you put this gas in the atmosphere, before the Earth could warm up, how much would the deficit in escaping radiation be? That's the term radiative forcing. Pre-equilibrium impact on it doesn't, you can't go and measure it directly. You have to know the radiative transfer of the atmosphere to calculate it. But we know that quite well. You can put these gases in a lab, measure the spectroscopy, put that into radiative transfer calculations and do a really nice job of that. So you could think of it as their net, it's the net force they have on driving global warming. This is their impact on global warming in aggregate. So the concentrations have increased by about a factor of 2.5 for methane since pre-industrial. We know that's humans. There are recent fluctuations. Maybe they are, maybe they aren't related to things like the gas boom. We don't entirely understand yet. And this is about a quarter, maybe a fifth of total radiative forcing, driving of climate change, the change in methane. So it's important. It's not the biggest show in town, but it's important. And we've seen this, we've heard this story before, how quickly we must reduce emissions in order to stay below 2 degrees warming. So I'm not going to go through this figure. This is just another of those calculations of what's the trajectory we need to follow to stay in a safe climate scenario. It's large reductions. And honestly, combustion of any fossil fuel in the long run is a problem if you dump the CO2 into the atmosphere. It doesn't matter if it's gas, doesn't matter if it's coal. It's a bad deal for the climate long term. We have to get rid of this stuff. All the sources need to be on the table. You can always say, well, look, the US, we're only 20% of emissions, and methane from the US, that's only like 5% of the total, and so it's a small amount, so we don't count, doesn't matter. Every source could say that, and then no one does anything, and then we get nowhere. So all the sources have to be on the table. There's no one that wins. And we need to manage in a way that weighs these equally. If we put all the force on one and not another, it's like whack-a-mole. The emissions come out somewhere else. Can we do that? Yes. We know that we can. We have the technology. This is in the literature. I'm not going to spend a lot of time on it, but it leads me into the topic of our discussion. This is an idea that a couple of Princeton professors argued, and it's been adopted, the wedges idea. This is a cartoon of how emissions might grow into the future if we do nothing, greenhouse gases versus time. And each one of these little wedges is some technological approach we could adopt to reduce those emissions. The technology we have is sufficient to get things to level out for sure. And then hopefully by a few decades down the road, we can drag it the rest of the way down as technology grows. And this is don't read this, you probably can't anyway. This is Sokolow and Pakala's list of their 15 wedges, and they said each one of these things we could do, and this is what it would be, and this would reduce roughly an equal amount of greenhouse gas emissions. One of them is replace coal with natural gas, which is what we're here to discuss. And another is photovoltaics replacement for coal, which we'll hear about later in the afternoon. And so Zach and I are going to drill in more to, sorry for the pun, drill in more to the coal natural gas question. So why might gas be better than coal? You probably all know this, but the energy produced by burning gas releases about half the CO2 compared to the energy produced by burning coal because of the composition of the material you're burning. There's less carbon in CH4, more carbon double bonds in coal. But natural gas is mostly methane, and it's a powerful greenhouse gas. So if it gets into the atmosphere, that can negate that effect. And so how much leaks is a big deal. Is this really a good wedge or not? Another reason to get at this is we need levers to pull in the short term. Methane is a very potent greenhouse gas on a short time scale, order 10 to 20 years. 10 years, it's mostly oxidized, and it's not in the atmosphere anymore. But for those 10 years, it's extremely radiatively active. So if we can reduce those emissions fast, we have a very rapid impact on short-term climate change. So it's a good lever if we can get at it. And finally, we need to know this because if we're going to have policies to manage and we don't really know what the emissions are, we're going to make mistakes. If we don't know what the emissions are and we regulate to reduce something, we miss something else, that's bad. If we want to make a carbon market and we don't know what the emissions are, how can you have a market when you don't know what you're paying for? That's not going to work. So we have to know these emissions. So how do we do this? We know the global budget from the atmosphere. We don't know the total amount of methane emissions from adding up all the parts. We know it from the atmosphere, from the concentration globally. Each individual part, our best estimate, however, comes from those bottom-up inventories, and there's a mismatch between those. If you look at any one source or any one region, you can have a large amount of leeway and still get to the right global total. So while we know the global total and we know the global source and sink fairly well, we don't necessarily know the parts that go into that also well. So here's an example. There's more here than you care about, and it doesn't show up very well. Fossil fuel emissions, agricultural and waste, wetlands, and then oxidation from the from OH in the atmosphere. There are many roughly important sources around the planet. And if you could see those numbers, you'd see that each one has an uncertainty of about a factor of 2. Because what we know is we got to match this number for the removal rate to show that that concentration goes up at the right rate. So we know the sum, but we don't necessarily know the parts. You could take 105 and 188, and 105 from here, 188 from here, or you could take the lower end of the fossil fuel and a higher agriculture value, or a high fossil fuel value and a lower agricultural value, you get the same total. And it all works out in the global balance. So that's why we have trouble with knowing what some of these individual pieces are. There are parts that we know well. If it's a big point source like a landfill, you know where it is and you can go measure it, you can go back and measure it again, you can go back and measure it again. That's not so hard. If it is hundreds of thousands of leaks from tens of thousands of components of the natural gas system, you can't go measure that all directly, one part at a time. And leaks don't tell anybody, right? That's why they're leaks. So they don't report. This is hard. So how do you make an inventory? This is the recipe for an inventory to do the bottom up. You have some sort of a count of how many devices like wellheads or actions like liquids unloading go on. You have an estimate of how much emission happens with each one of those things. You multiply that and you come up with a total amount of emissions. Sounds cool? It is. It's very useful. And this is work that was funded actually by EDF to try to update our emissions from the natural gas system with new technology that's around with hydraulic fracturing. And there's all these different pieces of the well system, and David Allen and colleagues went out and measured all these different parts, and I'm just going to circle pneumatic controllers used for the flow. And they measured 305 of them across 4 regions of the country, and they went out and measured them each once. How many pneumatic controllers are there out there? There's lots. And how long are they running? For years. They measured a lot. 305 measurements is a lot of work. But it's 305 point measurements of something that has numbers of tens of thousands going continuously. And if you missed something, if your list doesn't have something, you're biased low because you never counted it. So this is the hazard with relying solely on the inventories. Not that they're not useful. They're extremely useful, but they're limited. They can't do everything. Don't read that table. But look at this graph, because it has the same information. This is basically the EPA, this is a little complicated, EPA assessment of emissions in the year 2011. Every one of those bars is an EPA estimate of emissions from natural gas system in the year 2011. It comes from different EPA reports. This is the 2013 report, the 2014 report, etc. And these are different parts of the system. So production, you can see, their estimate has changed by a factor of 2 because they're not really sure what the right numbers are. They're doing their best, not knocking the EPA. but we don't really know those numbers that well. Our knowledge improves. This is probably getting better with time, but there's a lot of uncertainty. Don't take those things down to like 4 significant digits. It's in the calculation, but it doesn't mean anything. So how can we do better? I'm heading towards Zach now. We can make atmospheric measurements that are region or source specific. I said we know the whole planet from atmospheric data. If we can isolate our atmospheric measurements around some part of the system, we can then measure the emissions from that part of the system, compare it to the inventories, and try to learn something. And they don't agree, and you go back and forth till you come to convergence. And so I'm going to tell you bits of a EDF-led study. Too bad Andrew isn't here yet. He would like that. Oh, he is here. There he is. That's fine. So I'm going to pitch your company's work, your organization's work. One way you can do this is to go downwind of something like a gas well. And you measure a gas that you release, like N2O, you measure its concentration downwind, and you measure the methane concentration downwind. Then you can back out how much methane must be leaking from this. And you can do that, say, a well facility at a time. And that's a whole bunch of components that you measure all at once, site by site. So that's one approach of atmospheric measurements, site level. The other is you could take an airplane. This is northeast Pennsylvania, in case you don't recognize the geographic boundary there. And you can fly an airplane in a loop around thousands of wells. And you measure the concentration of methane downwind of those thousands of wells, and you back out what the total emissions are. And so EDF has sponsored some of this work. Some of this was funded by government agencies, and then EDF led a synthesis of data of this sort from around the country. And this is the site-by-site building up. So you have 100 of these sites that you measured. You extrapolate over 1,000 of them. You compare that to the aircraft data, and that works out pretty well. That's not using the EPA inventory. Those two seem to agree. But when you compare that homemade bottom-up inventory to the EPA numbers, 13 doesn't equal 8. There's more emission that you see from the atmosphere than you get from the inventory, about 60% higher. And so the conclusion there, 60% higher emissions than the inventory estimate, likely because the inventory methods miss things that aren't in the inventory, some kind of abnormal operations that's not on anybody's checklist to measure. And for the nation, that's methane leakage is about equivalent to the CO2 emitted by burning the natural gas. So that's about equal impact to the CO2 that you emit. So it's just about a wash relative to coal if you don't consider the coal methane leakage, I think. But that's national, and that's 20 years. So a 100-year time frame, it's still better than coal, and that's the whole country. Zach will tell you more about Pennsylvania and West Virginia, where the answer is different, interestingly. A couple other messages. A small number of sites tend to be responsible for a large fraction of the emissions, which implies that if you could find the ones that are busted, you could make a lot of improvement fast. And second, this is the thing that I was leading towards with Zach's results, the gas basins with very high production, like the Marcellus, tend to have a smaller percentage leak rate. They are better for climate, it seems, from the data. Here's one example that stuff Zach isn't going to show. This is the cumulative emissions. This is a complicated figure. But basically it means this is the number of sites you measure as a percentage, and this is the total number of fraction of emissions. So when you get to 20% of the sites, you got 80% of the emissions accounted for. So 1/5 of the sites are responsible for 4/5 of the methane leakage. So there's a small number that are dumping it out. If we could find them and fix them, that'd be great. So some conclusions. They're both fossil fuels. In the end, this doesn't solve the problem, honestly. Every time somebody says gas, bridge fuel, I think, damn, another fossil fuel. But it could help. I mean, in the near term, this can help, and Zach will show some results from that. And we got to go after all the sources. You can't say this isn't this greenhouse gas source's problem, because there's lots of small sources we have to interrogate. We have to be holistic. We can't just say, gas industry, do better, nobody else has to worry about it. That'll cause perverse incentives and cause trouble. There are the technologies that exist now to make serious progress. We need more measurements to understand what these sources are. And at that, I will hand off to my colleague, Zach.
All right, let's get down to business, guys. So I'm going to be talking specifically more along the lines of West Virginia natural gas. And to do that, I think it's first best to understand how the heck did we end up measuring methane from West Virginia? Why did we decide to go down here and study this region? And it all has to do with our study in northeastern Pennsylvania. So this background right now, this is just a methane model. It's a weather model that's forecasting methane emission or methane enhancements in the region. And all we wanted to do at the time was look at northeastern PA, where there were a bunch of unconventional wells. There was nothing else in the region, and we just wanted to understand what the methane emissions were from them. So we flew around the region, but something kept happening anytime we had a southwest wind. We ended up seeing signals that just made no sense whatsoever. And so it wasn't until you ran the model that you really saw what was going on. There's this blob of doom coming out from right where we are right now. And it's just this enormous concentration of methane coming from this region, and it completely disrupted our study, and that was obnoxious. So we had to go and we had to look at what was going on down here. All right, I was good with the northwest winds, but so it's actually a really cool region if you like methane. That wasn't funny, but okay. Oh boy. So it's a really neat region, this circled area right here. You have unconventional wells, so fracked wells, horizontally drilled wells. These produce a huge amount of natural gas in the Marcellus. This circle right here is responsible for pretty much half of the Marcellus production. In addition to this, you have conventional wells in this area. Not too many, but these are older, vertically drilled wells that produce pretty much no gas whatsoever. And then finally, in this area, you have coal mines. We often think of coal mines as being dirty in terms of the CO2 emissions, but coal mines actually have methane associated with the production as well. If you go into the EPA's inventory and look at the largest point source emitters in the country, they have a list of like 600 of them. Here's 8 of your top 10 right here. Coal mines located in this circle. So these are actually legitimate sources of methane emissions. And so when you look at coal itself, in terms of the whole country's methane emissions, it's only 8%. That's significant, but I mean, when comparing to animal agriculture or natural gas, it looks like a pretty small piece. But when you look at West Virginia specifically, you pretty much only have 2 sources here of methane that you really care about. You have coal and you have natural gas. And so we wanted to look at that region that I showed and try and verify or see if the methane emissions that we were expecting in the region turned out to be accurate or if the inventories appeared to be a little bit off. So the University of Maryland flew 6 times in 2015 and 2016 and gathered a whole bunch of methane data in this region. And what's normally done with this is you have an upwind transect, you have a downwind transect that's downwind of the wells and the coal mines, and you just perform a mass balance. You figure out how much methane must be coming from inside your box. But we at Penn State like to torture our grad students, and so we have a much more complicated but efficient approach at solving for methane emissions. And I'm going to start by showing northeastern PA examples, because it's much easier to start with that. There's only natural gas in that region, so we can look just at that. But it's going to be a 3-step approach to solving for the methane emissions. You get the methane observations. You already saw that part with the aircraft. But what we're going to do differently then is we're going to put emissions into a weather forecasting model. And this model, it's just a normal weather model. It has wind and temperature and precipitation. And what it can do is it can forecast these plumes throughout time. And what we're going to be trying to do is we're going to adjust the emissions inside the model until your modeled concentrations end up matching your observed concentrations in the atmosphere. And so by doing that, we can get a good understanding of the total emissions coming from individual sources. And the really neat part about the model is that it's not just one big blob you have to look at in the model. In the model, you can assign different sources different tracers. So we can look at plumes specifically from unconventional natural gas and plumes specifically from coal or animals. So that ensures that when we're looking at a plume in our aircraft observations, we can line it up with the actual source that we're trying to solve for and make sure we're not mistaking it for something else. So this is a really simple example in northeastern PA where we only really have to worry about unconventional gas wells. So this is May 29th. The wind was blowing south to north. Here's all your wells as the black dots. And these colors on the aircraft represent methane enhancement. So you can see you have an enhancement downwind of the wells. So just eyeballing it here, this looks like science is working on this day. This is the same thing, just as a line plot showing the methane enhancements in a clockwise rotation around the aircraft. The first thing we do is we go to the model and we look at all of the sources not related to natural gas in this case. So here on the western edge, you have an animal agriculture plume from Lancaster County. And on the eastern side, you have a landfill from the Scranton-Wilkes-Barre Urban Corridor. And what we're going to do with these non-natural gas sources is we're going to subtract them out of the observations. So now, theoretically, all that should be left is your observed natural gas enhancement. And you can see now that pretty much the only place where we see an enhancement is downwind of the well. So again, science looks like it's working here. So finally, we're going to go into the model, and we're going to look at the unconventional natural gas plume inside the model. And so to do that, we create a first guess as to what this plume is. We use an emission rate of 0.13% of production, and we see what kind of plume that would create in the model. And we can see here on this day that the model ends up being lower than the observations. But it's really neat. You can just scale the concentration in the atmosphere with the actual emission rate. So if we have to adjust this by a factor of 2 to match the observations, then that means that the emission rate just has to be adjusted by a factor of 2. So on this day, we would say the emission rate from unconventional natural gas production is about 0.26% of production. So that's Northeast PA, and I promised to talk about West Virginia. So let's go back to this disaster right here. We have coal and unconventional wells as the two main sources of emissions in this region. And you could just do what we were doing previously, but now we have to adjust both coal and unconventional gas in the model. So here's one possible solution. The blue is the observations, red is the model. You can see we do a pretty incredible job lining up the observations with the model. And here we do it by using a coal rate that's 1.8 times the EPA's expected emissions and an unconventional natural gas rate of 0%. Now right here, I could have stopped my work, I could have published it, and I could have gone to work for ExxonMobil. But I decided to make this second slide as well, where you can get an equally great solution, but this time you're now using a coal rate that's exactly what the EPA is expecting, and an unconventional natural gas rate of 1.6% of production. So you have two completely different solutions that give you a similar matching observation set. So we have to dig a little further in order to figure out how much coal versus gas is associated with these emissions. And to do that, we can actually look at ethane. Different sources have different ethane to methane ratios released with them. So for coal in West Virginia and Southwest PA, there's pretty much no ethane inside of it, whereas the natural gas in this area has an ethane to methane ratio of about 7%. And then cows and landfills, they just have 0. It's a different type of source. So we take that ethane to methane ratio and we can look at continuous ethane to methane observations from the aircraft. We can look at the plume and see what is the ethane to methane ratio inside this big coal and gas plume. So when we do that, we see that the mixed coal and gas plume seems to produce a ratio somewhere between 2 to 3% ethane to methane. So now all we have to do then is plug in those ethane to methane ratios for the individual sources and see what combination of coal and natural gas will produce a mixture that we saw in the observations. So going back to that one day we looked at, a coal rate of about 30% greater than what the EPA was expecting, and an unconventional gas rate of 0.9% of production gives you a mixture that falls within that 2 to 3% ethane to methane ratio. So by optimizing both the methane and the ethane to methane ratio, we can sort of sort out different solutions for the coal and gas emission rates. Now, doing that for one day produces a wide range of emission estimates, but what we can do is we can go back through the 19 different transects we have and look at where the solutions end up overlapping. And I know this is a messy graph, and it's very colorful and pretty, but the main story you just need to take away from this is the overlap where the most convergence occurs between the different transects states that the coal rate is about where the EPA expects, plus or minus about 40%. And this result isn't too surprising because the EPA requires measurements of coal ventilation shafts due to safety reasons 4 times a year. So we should actually have a pretty good handle on methane emissions from coal mines. Natural gas, we found, the unconventional natural gas leak rate was about 0.5% of production. Anywhere between 0.2 to 0.8% was our range. So what does this number actually mean? When you look at other basins, you see a wide range of emission rates that have been found. They're anywhere between 1.3% to sometimes numbers higher than 6 or 7%. But only in the Marcellus do we see rates that are less than 1%. And not just less than 1%, we're talking about 0.5% leakage rate here. So these are very efficient wells. Just really quickly, what does the EPA expect should be coming from these wells? On a national scale, the EPA expects your emissions from production are about 1%. But when you look at West Virginia specifically, the EPA actually thinks the emission rate should only be 0.1%. So it is a low emission rate, but it's actually higher than what the EPA is expecting. So it's kind of a mixed message there. But we're going to focus specifically on what the emission rate of 0.5% means in terms of total greenhouse gas impacts. But first, let's try and understand why the emission rate is so low. And to understand that, we can actually look at West Virginia, where you have a case of 2 completely different types of wells. You have the unconventional wells, which I've been talking about, which we were studying. These are the horizontally fracked wells. And you have the conventional wells in West Virginia, which are much older. There's about 10 times more of them. And when you compare them side by side, it's really cool. The average production per well from an unconventional well is so much larger than from a conventional well that you can't even really see the line on the chart. Unconventional natural gas, especially in this region, just produces incredible amounts of natural gas per well. There is no other well site in the country which can produce natural gas at this kind of rate per well. When you look at the average methane emissions per well, it should be no surprise that the wells which produce a lot more methane have a higher overall methane emission associated with them. So here, the conventional wells don't have nearly as high of an emission. But when you normalize this to production and you see the true efficiency of the wells, this is where you can really see the unconventional wells in this region really perform really well. So again, the unconventional natural gas emission rate that we found was about 0.5% of production, whereas the conventional natural gas has been found in a different study, which measured them specifically. He found them to be about 13% of production leaking out into the atmosphere. So that's a lot of numbers thrown at you. Let's conclude this by just looking at a table of what this means for the actual greenhouse gas emissions in West Virginia specifically. So when you look at where the energy comes from, this is just where the energy is. Coal and natural gas are pretty much the 2 major energy producers in West Virginia, and it's close to a 50-50 split. But you'll notice that most of that energy comes from, most of the natural gas energy comes from natural gas, unconventional natural gas, and not conventional wells. However, when you look at the raw methane emissions associated with each of these sources in West Virginia, I mean, here's coal right here. Coal is actually the largest source of methane emissions in West Virginia. But perhaps the bigger story here is the difference between the unconventional natural gas and the conventional natural gas. Because even though the conventional natural gas produces very little energy, it's producing a much larger amount of the methane emissions. And so if you actually wanted to break this down into methane per unit of energy produced, here's coal here. It's really, I mean, natural gas is twice as effective here compared to coal. Unconventional natural gas, I should say. But the conventional wells are just like really, really bad. That's a polite way of putting it. And it's just because they don't produce much gas. They have large leaks associated with them. So an overall efficiency level for them is just incredibly poor. But that's only half the story. There's CO2 emissions related to the combustion aspect as well. So we have to throw those in there as well. What happens when these different sources are inevitably combusted? So it's been said multiple times, coal has twice as much CO2 released when combusted compared to natural gas. And you can see how big these numbers are compared to the CO2 over a 100-year time scale. So when you add this all together, what you get is that unconventional natural gas produced in West Virginia is pretty much twice as good as energy produced from coal. So any conversion from coal to natural gas, specifically unconventional natural gas, is going to halve your emissions. And that's a really big number. To reduce something by half is we're usually talking small fractions when we're figuring out how to save, how to reduce greenhouse gas emissions. So that's a really big deal in the short term. Note that any energy derived from conventional natural gas, it's not a large amount. We derive very little energy from conventional natural gas here. You're really not saving any greenhouse gas emissions here. The key here is if you're going to make this switch, you need to make the switch relying on high-producing natural gas wells, not things like conventional wells. This is just the same thing with CH4 now weighted over a 20-year period instead of a 100-year period, where CH4 now becomes more dominant. And your story between coal to natural gas isn't changing. Coal to unconventional natural gas is always going to be about twice as effective in this region. But here you can really see the conventional wells just, they become an enormous source of greenhouse gas emissions. So the main takeaways from this, unconventional gas produced in the Marcellus has some of the lowest methane emission rates in the entire country. And this is mostly just due to the fact that they just have incredible amounts of production per well. There's no other wells in the country that can compete with the Marcellus unconventional wells in terms of natural gas produced per well. So this just makes them naturally more efficient. That said, the EPA is still underestimating these emissions by a factor of 2 or more, but it's still a low number overall. West Virginia produced coal has twice the greenhouse footprint compared to unconventional natural gas. There's really no way around that. There's no amount of uncertainty you could throw in this at this point. It would be really hard to find a situation where coal in West Virginia is going to outperform natural gas in terms of greenhouse emissions. I note one caveat: the study did not look at emissions coming from the distribution sector of natural gas. So when it's being distributed to wherever it's going to be used, there's huge leaks, it could theoretically end up being worse than coal, but you would need enormous errors in the EPA's inventory for West Virginia coal to end up outperforming natural gas. Finally, the low-producing conventional wells in this region, they exist in PA and other regions in the country as well. Low-producing conventional wells, they're very inefficient, and they end up creating these large contributions to the methane total while producing very little energy for the state. There's very little gained by keeping these active. And then finally, and this is always important to stress, because it's kind of opposite to what what the main messages up here are, natural gas can be a short-term gain to the environment. You can make this switch over quickly, and you would see great short-term gains in terms of your greenhouse budget. However, it cannot be a long-term solution. Efforts must always be made to come up with a roadmap towards a carbon-free energy future if you're going to achieve the goal of essentially eliminating greenhouse gas emissions, because natural gas is still a fossil fuel, even if it's a cleaner one. Yes? 8 slides. This is why I need slide numbers. This one? Okay. There we go. Yeah. Unconventional natural gas wells, yes. I think that now. Let me know. I work in PA. That's not. How many are there? So they're associated mostly in just 2 counties in West Virginia. 1,200 pads. Sorry, pads. Are you? I might have meant pads here, but I'll have to look. My numbers are always for Pennsylvania, and then I convert the number. I have the total methane generated from these wells, so that wouldn't affect any calculations. But I'm willing to admit that I may have totally screwed up the number. It's about a 10-to-1 difference between conventional and unconventional in terms of numbers. What was the other? Yes. In West Virginia, they sort by horizontal versus vertical drilled wells. It's possible that some vertically drilled wells are fracked as well. That information is not provided by West Virginia there. But for the part of conceptual knowledge here, yeah, that's going to be the difference between those two. I'm not supposed to be taking questions now. Is that okay? I just... Okay.
So next we're going to have Derek Johnson. We're going to hold the questions until the end. Devin back there can hand out the 3x5 cards. If you need a 3x5 card, raise your hand. Devin will also pick them up, bring them to me. And so at the end of after all 5 panelists have presented, then we'll have some questions and some interaction among the panelists. Next is Derek Johnson from right here at WVU. Since we started, Andrew Williams from the Environmental Defense Fund, EDF, has also joined the panel, and he'll be following Derek.
Well, I missed the memo about coal, so some of my comparisons are going to be to diesel for the transportation sector. I'm with West Virginia University, a group called CAFE, and I'm going to present some of the data from our recent studies from across the natural gas supply chain. Again, also, some of our studies have been funded by the EDF, NSF, Department of Energy, and NETL. For those of you that don't know CAFE, it's a group of about a dozen researchers in the mechanical engineering department here at WVU. It's actually been around for 30 years, completed over $100 million in externally funded research. If you do know us, you may know us for our heavy-duty diesel vehicles and engines, but we have a lot more than just that. Specifically, I've been focusing on natural gas vehicles and engines, and then some atmospheric emissions separate from the engine exhausts. This is just a list of projects that I know that I've been involved with, and again, we have researchers involved with far more than this, but I just wanted to look at some of them where we focus on the impact of increasing natural gas utilization for, let's say, heavy-duty transportation or prime movers in unconventional well development, and where we focus on the impact for methane emissions if we do these conversions. So the first one was funded by EDF, and along with industry partners. Our goal was to complete a nationwide campaign to get a full pump-to-wheels understanding of methane emissions from the current heavy-duty technologies. So you'll notice this isn't a well-to-wheels, so we're excluding anything before the pump. So it's once we get it to the pump, the compressors, the LNG storage tanks, the nozzle disconnects, the vehicle tank systems, all those components. Again, this was right in our wheelhouse because we did a significant amount of chassis testing and in-use vehicle testing of refuse trucks, transit buses, short-haul, long-haul trucks all across the U.S. But the atypical non-exhaust emissions were somewhat new to us. So we developed this full-flow sampling system to accurately quantify that. Provided us with a little bit more flexibility than the old high-flow sampler that most of industry uses. So in the final study, we had data from 22 vehicles, 8 CNG stations, 6 LNG stations, and LNG vehicle tanks and LNG station tanks all across North America. And again, our goal wasn't really to say what a national estimate is. It's to take the current data and then, as engineers say, where could we go from there? Again, that key threshold from a previous EDF study, looking at that 1% threshold for the heavy-duty diesel vehicles to switch to natural gas. So the key findings from this multi-year campaign, you see in the upper figure here. Can you guys see that? I'm not very good with it. Oh, this one? So you can see in the upper figure here, we have just a sample of data from multiple vehicles, and we actually broke it down by vehicle type, engine type, activity type. All these vehicles behave differently, and that could affect their, impact their emissions profiles. Again, keep in mind that target is 1% wells to wheels, and we're just looking at pump to wheels. So you can already see that the in-use data of current technology vehicles, many of those are above that 1% threshold on just this portion alone. And if you dig deeper and look at the bottom of the overall distribution, most of it is coming from the engine exhaust. But we also found that the engine crankcase is often overlooked. And for the spark-ignited natural gas vehicles, it's open to the atmosphere. So it's one of the easy things you can do to reduce methane emissions. Not included in the final study were some results of dual fuel conversions. Now, there are dedicated dual fuel type engines that are heavily integrated and sold to market. And then there are these aftermarket conversions that are much cheaper. But what we found was that of the partial fuel substitution you were putting into the engine, depending on what kit and what engine and what activity range, you would lose 3 to almost half of that fuel out the exhaust. So not very economic. Another thing is that goes beyond just technology is manual venting. Manual venting of LNG tanks. LNG allows the vehicles to travel for longer distances, which is important for long-haul trucking. But some of the technologies, as the LNG starts to heat up, it boils and increases pressure in the tank. Some of the very early stations couldn't do anything with that vapor, so you just had to vent it off when you refueled. Most stations now can handle that, but it's more of a practice, is getting those older drivers who were dealing with the first generation to stop that venting, because they may think, oh, this is going to make me fuel faster, but I'm losing my company 4% of the fuel they just paid for. And then again on the bottom, you see that most of the station emissions or leaks or things like that are fairly low compared to the vehicles. So the vehicles, the current technology vehicles, were the big things. We also took some data and modeled again for the future. And one of the key important things for fleets that want to use LNG is to design their fleet or partner fleets adequately with the stations so that the vehicles don't vent and the LNG stations don't vent. If you have a mismatch, it may throw off that balance. And then, really, since the study was completed, Cummins has actually closed their engine crankcases, so they've cut their numbers down almost by half. But to really target that exhaust, we need future research on improved natural gas engines and catalysts to further reduce that methane. So, jumping on to the next study, also funded by the EDF, we were one of the teams that played a small role in this 2-week campaign in the Barnett region. Our specific goal was to take this new system we developed to quantify non-exhaust methane emissions and to assess contemporaneously with all these other programs what the direct methane emissions were for some compressor stations and storage facilities, because these are typically one of the big point sources along the natural gas supply chain. So we did that. Some of the key findings, again, they had other much larger studies that did this, but they were at different locations or different times. So we wanted to see if we took measurements while these other measurements were going on, if there were any outliers or anything crazy going on. Again, from the 5 sites, they were emitting 94 kilograms per hour. And some of you may look at that and say, wow, that's a lot. Well, it is a lot, but it matches the other studies that they've done. So about 20 kilograms per site. There wasn't anything out of the ordinary at these sites. Again, looking at where a lot of studies focus, a lot of people worry about leaks. Well, you can count up the things that we classified as leaks, and it's only about 13% were leaks. The major sources was the engine exhaust. So these compressor stations have natural gas engines. Makes sense, they're using the fuel that's on site. But they're losing some of that exhaust or methane out the exhaust. And they also had open crankcases. So the open crankcases could easily be closed. That's 5% reduction. But as far as the engines, these are pretty old engines, very expensive and large, so there would have to be new technologies developed for that. And then from an engineering perspective, I'm a mechanical engineer, I think very practically about these things. If we know, this is pretty much consistent with other reports, and we know by design that they're going to continue to use certain valves or they're going to continue to vent their tanks to atmosphere, why don't we use that? Because it's not just methane emissions, it's wasted energy. So we could easily substitute that back into the fuel system and displace some of the fuel for that engine. Some places are actively flaring it, so that reduces its greenhouse gas impact, but they don't get any useful work out of it. So not a real benefit from an energy perspective. The next program, this one was funded by the Department of Energy. It was a few years ago that we started this, actually 2013, Rob? 2013, and that's when things were still moving quite heavily in the natural gas industry, and it was right before they started the downturn, and they want to know how to save money. So they had a lot of people addressing this through reducing their fuel costs. So there were two options. They could convert their Tier 2 diesel engines to dual fuel to displace 50-60% of their diesel fuel consumption, or they could get a whole new Tier 2 engine to drive their drilling rig or their stimulation pump and use dedicated natural gas. And we know that these engines are certified, but we don't know how they behave in the field, as most engines that are tested or certified don't behave at all like they do in the field. So we conducted this multi-year campaign working with industry, which isn't always easy. And you see us down here in Texas. This is a dedicated natural gas rig in the middle of nowhere, West Texas. So again, we were all over multiple shale plays trying to collect, again, a complete data set of the current technologies. And what we see is a similar story to the transportation retrofit kits for dual fuel operation. Again, we remember if those ones were 3 to about 50%, these ones are a little bit lower, about 14 to 22%. So 14 to 22% of the methane you're supplying to the engine that you think you're saving money is just going right out the exhaust. And, oh, the crankcase again. That's only 1 or 2% in these cases. But again, these are easy solutions. One of the big things as far as the concern of methane is, at least from a local perspective, is that we saw that the dedicated natural gas engines, they do produce methane, which is kind of what we're focusing on here. But one of the great benefits of them is that they reduce NOx emissions by a significant amount. So that can improve local air quality. So that's a kind of a trade-off that industry kind of has to assess, which is more important. And we see that here, that in this nice little graphic my grad student made for me. As we increase utilization, again, we want to increase the utilization to save on costs and hopefully have some emissions benefits, especially like the NOx emissions. But we need to find some way to reverse the efficiency and carbon dioxide or greenhouse gas emissions trends. We need to flip those. Because again, as you invest in these natural gas technologies, thinking that you are improving your emissions footprint, sure enough, your CO2 equivalents are going up. And the last project is another project funded by the Department of Energy and the National Science Foundation. Right here in Morgantown, we have the Marcellus Shale Energy and Environmental Laboratory, which is this well site shown here below, with Northeast Natural Energy. 2 of those wells were drilled during a huge measurement campaign, focusing on everything from ambient emissions to engine emissions, water emissions, everything. And what we've done is continued to take measurements at this site over time. As other folks have discussed, a lot of studies focus on, well, we're going to go to a lot of sites to increase our sample size, to get some geospatial variability. But a lot of that geospatial variability isn't geospatial, it's temporal. It's how different sites are being loaded or how active they are. So at this site, again, this site feeds all of Morgantown. So these 4 wells feed all of Morgantown. So it actually has quite an activity range for this region. Most wells are just opened up and they sell, but these ones are actually shut in, so we get a lot of different types of activity happening at this one site. So we're taking temporal measurements over time, about every 3 months, 2 or 3 months, we go and use our system to directly quantify those emissions. And again, to look at that temporal variability and to look at improving quantification methods, we're collaborating with Dr. Abdul Aziz, who couldn't make it today, he was under the weather. But we're trying to look at, again, deploying new techniques, state-of-the-art analyzers, and seeing how we can better improve the accuracy of measurements. So you see here, just again, some stuff that we're looking at. Again, trying to use that gold standard of having this historical emissions profile from this site. Not only do we have the measurements that we take, we have the daily water production, the daily natural gas production. So hopefully this will serve as a good baseline so that we can look at other methods, like other folks were talking about, indirect quantification methods at the site level, and see how we can infuse that data to reduce the uncertainty. So just some quick conclusions. You saw that multiple times I said engine crankcases. Engine crankcases are a source of emissions. Most of you probably have light-duty cars, right? Well, their crankcases have been closed for about 30 years. So it's an applicable technology that just needs to be implemented. Again, depending on what type of engine it is, whether it's lean or stoichiometric, you could easily cut your emissions from that particular engine by 5 to 50%. So that's something that we need to be. Now you can't just add it on and do it. It does take some technology, but it can be done. Again, improve training and practice for the operation of LNG vehicles, getting the truck drivers to understand they don't need to vent their tanks. But a lot of the future improvements and major reductions are going to require some more engineering research. So some of the engines that we showed here range from 9 liters to 50 liters, a variety of engines, and we've done other research I didn't cover on engines that you could hold in your hand. All of them, if you're using them, powering them with natural gas, have the same methane issue. So natural gas engines across all displacements really need additional research. And even if we can't complete the research to make a better engine, we have to do something about that methane in the exhaust to see the full benefit from that conversion. Again, as some of the colleagues discussed earlier, continuing research on quantification to better understand the problem. You know, they're kind of way up here and I'm kind of way down here. How do we merge those two together? And as those technologies or methods improve, that'll highlight more additional easy fixes. And again, from an engineering perspective, we just kind of scratch our heads a lot because we'll go to a site and we know where the emission source is going to be. So if we know where it's going to be, why don't we just implement some simple engineering design to capture it and use it? So I think that's all that I had. So thank you.
Next, we're going to have Professor Fershee. He's a colleague here at the College of Law who's done a lot of research in the area of methane emissions, particularly with respect to wells in West Virginia and Pennsylvania. Professor Fershee.
All right. Well, I'm glad I could be here, and thank you all for sharing the science. Anything that looks sciencey is not my fault. Actually, it is my fault, but I didn't do it. I stole it from other people. There's some EDF stuff in here. My background, I teach here at WVU College of Law. I work with Jamie at the Center for Energy and Sustainable Development. I also work for the Center for Innovation and Gas Research Utilization, a name that was also not my fault. Working to look at how we can work across disciplines at the natural gas that we're having here in West Virginia and what the opportunities are in limiting the harms. What I want to talk about today has to do with legacy well emissions and the challenge that we have with old wells. And we saw that from some of the stuff that was presented already of abandoned wells and legacy wells. And this is not to say we shouldn't be looking at emissions at other wells and other places, but as a theme in my work, I have a tendency to start looking at things that other people aren't looking at. And we have a lot of people doing research on fracked wells and new well sites, but I think we're missing part of the story. And I think there's actually a real opportunity here, but we lack some incentives to do something about it. And so that's one of the things I want to talk about here. I wanted to start a little bit with talking about some framing, which I know that this morning people were talking about, of how we look at a lot of these things, but one of the reasons that I think we're having trouble with legacy wells and old wells is how we tend to think about energy as a general matter. This is one of my favorite polls, and I put favorite in quotes. This was a poll that was done by Pew right after Deepwater Horizon, within months. And they said, should we be doing more coal, oil, and gas exploration? And 68% of people still said yes, even though oil was still spilling into the Gulf of Mexico. Yet 71% also said we should do whatever it takes to support the environment. Notice there's a bit of a disconnect between those two potentially. 58% we should be drilling on federal land. 56% said stricter environmental laws and regulations are worth the cost. That number, by the way, as of last year, is up to 59%. So there is some trending in the right direction. One of the things that we tend to ask, though, is always forward-looking. And so here, for example, we saw this that says we should be doing all of it, right? Let's do everything, all of the above. We've heard that quite a bit. Here we say, well, if we pick and choose, should we do solar? Well, 89% said, I support doing solar. 83% said we support more wind. And then as you work your way down, 45% of offshore drilling, 43% support more nuclear plants, 42% support hydraulic fracturing, and 41% support more coal mining. As you might imagine, those last two probably are not reflective of West Virginia in terms of those poll numbers. But we have, as a national policy, we tend to look at those renewables. This is one of the sadder ones in terms of how we look at this, and because we're looking at climate and emissions. In 2009, 49% of people said, I believe climate change is because of human activity. 36% said because of natural patterns, and 11% said, I don't think there's any solid evidence. Fast forward 5 years, now 50% believe that humans are a cause of climate change, but now only 23% think it's natural patterns, and apparently that some of that 23%, or most of that 23%, has jumped over to say there's no evidence. That's not very good progress, which shows us a lot of challenges and hurdles that we have to get over. When we deal with legacy wells, it's particularly hard because we're going back to try and work on something that doesn't do anything for us. As we've seen with our prior folks, this region is a huge region for all sorts of oil and gas, and it's huge for shale gas wells. But if you look at this map, and you can see the yellow areas are areas in current shale production, and the kind of grayish areas and the yellow areas combined are where oil and gas activity have happened. So what we see largely here is that the oil and gas regions, whether it's for fracking or not, tend to be oil and gas regions. So we have oil wells and other things in these areas from a whole variety of different places. So when we think about law and policy, we have a tendency to focus on, one, what's new, right? We need to think about things that are right in front of us. We have a tendency to respond to things that are obvious. It was a lot easier to restructure MMS after Deepwater Horizon because we saw burning and oil-covered birds and, oil-covered shrimp. I mean, you see it, you respond to it. So we respond to what's new, we respond to what's obvious, and then we often do something, we go out and we make a rule. And this is one of the things that I've seen related to hydraulic fracturing. I taught at the University of North Dakota starting in 2007, so I was there for the oil shale boom out there and watched the response to how we do things. We're very good at making rules when we see something. When it's new and it's obvious, we're quite good about deciding to make a rule. What we're not great about is enforcing rules. We're not great about following through on those. And that's a big problem with our abandoned wells. Now, related to this, and we've seen some of these numbers, but I like these slides. My colleague Tim Carr in Geology and Geography Department put these together. The red is the amount of gas production coming from shale gas wells. The blue is the production from conventional wells, which I think in this context does include fracked wells, but vertical wells, all vertical production. The blue here are the number of conventional wells, and the red is the number of shale gas wells. And so if you start putting together the data that we were seeing earlier, the amount of emissions that we see from conventional wells and the emissions that we're seeing from new wells, the numbers are pretty staggering. When we talk about oil and natural gas liquids, we see the same thing, right? This large number of production coming from the red part with horizontally drilled and fracked wells, and the blue part from conventional. This is the number of wells that we're looking at. This is just, these are West Virginia specific numbers. So if we know we're getting emissions from both kinds of wells, and we know that the emissions from conventional wells tend to be higher, focusing on the red is a problem, especially because we get very, very little from the blue, right? They don't do a whole lot for us. We're getting gas from these fracked wells and oil and natural gas liquids, so at least there's something that is being productive. So what I would suggest is that we have a near-term bias. So and look at EDF's numbers. We have reported emissions of 112,100 emissions from those unconventional wells. The conventional wells, we've got nothing. These numbers look at around 253,000 emissions from the conventional, more from unconventional, more from the conventional, and I think there's some argument that those numbers are, that this number is actually even higher writ large. In West Virginia, we have 144,000 permitted wells. We have abandoned wells laws. If you're curious about what the law is, the Abandoned Well Act is Section 2210-2. We have an abandoned well rule at 356-1. We have rules for plugging that are codified in our laws, Section 22-623. We have the rules. The question is, are we going to plug the wells? And that's the challenge that we're facing right now. In West Virginia, we have 12,491 wells that are listed as abandoned. We have about 55,000 unidentified. Unconfirmed. And so we have companies that want, well, I'll talk about that in a second. Let's take a look at the open well inventory in this region. Kentucky has 32,500 orphan wells. Orphan wells are wells that we don't know who drilled it, we don't know who's responsible for it. Right? These are usually, in most of the areas, pre-1960s, when we started actually saying, oh, you're going to put something in the ground, let's record that happened. But when you have wells that have been drilled in Pennsylvania and Ohio since the 1850s, these numbers are problematic. So 32,500 in Kentucky, just 737 in Ohio, 4,458 in West Virginia. The next slide is the one that shows you our problem. These are the budgets to deal with those. Right, 950,000 in Kentucky to deal with those 32,050. 737 wells in Ohio. They actually upped that to $15 million this year. West Virginia, $385,000 to deal with 4,458 wells based on this number.
And just say, I actually worked on this story where we pulled these from. Just to say, in Ohio, a lot of that number is still low because they haven't identified.
Yes.
They're doing huge inventories to try and put more on the list. That's the catch.
Absolutely correct. These are the ones, this is what they know. But that number suggests that they very much are planning ahead, right? But it's pretty staggering to look at the budgets that we're talking about. And the numbers don't really get better. So as we talk about these old wells, again, we have 700 plus known in Ohio. Pennsylvania estimates between 475 to 7,000 to 700,000 abandoned wells in Pennsylvania. Pennsylvania is looking at those emissions, by the way, at 5 to 8% of the total greenhouse gas emissions for the state coming from those. And so this is a project we should be focusing on, particularly, again, because we get nothing from these wells except waste emissions. These are not productive. These are not helping people. These are not powering vehicles. These are not powering. All they're doing is creating a problem. Pennsylvania has done some research looking at this. They inspected 136 wells. They found 8 of them were leaking, which in one sense seems like pretty good numbers, but this goes to the problem How many wells can you get to? Are they leaking in a particular time? This last part is another problem that we see in West Virginia, is the free gas problem. And if you know anything about how oil and gas works, old wells, you don't tend to see it anymore. Old wells, somebody say, I'll come drill a well on your site, and they say, not only will I pay you a royalty for doing this, but we'll give you free gas. We'll run a line right to your house, which, by the way, is often not very safe. Various parts of West Virginia, if you go out, there are people who are still getting free gas, and it might just be a PVC pipe that's running from an old well right to their house. It's emitting at both ends. There's very little gas there, and there's two reasons that people want that. First, the homeowner may be using that gas, or at least likes the idea that they could, right? My gas, my methane emissions, I get to keep it. The other issue is that some lease owners are using that to try and keep the land available in case they want to go back and drill again. Right. Now, historically, it goes into oil and gas law, that typically you have a certain amount of time to drill, usually 2 to 5 years, used to be longer, but 2 to 5 years when somebody gives you give a lease, they have 2 to 5 years to start producing. Once they start producing oil or gas, as long as they're producing, that lease stays with them. Oops. The whole time. So it can be 100 years old, and some of these wells have been operating and producing for 100 years under the same terms as the original lease, except West Virginia did fix it to say you have to get at least a 1/8 royalty in terms of payment. But some of these places, they're not producing. They're not selling gas. All they're doing is letting that free gas run to the homeowner. That keeps, at least in theory, that lease open so that they could come back. Now, actually, if the homeowner were to fight it and say that's not in a producing quantity, they might be able to get out of it. But of course, most of the folks keeping free gas running in a PVC tube to their home aren't going to consult a lawyer to go through this process. And so there's another educational campaign that actually could create some opportunities to start plugging some of those. But then you have to convince a homeowner to give up their free gas. And that's not always an easy conversation, as you might imagine. This is what some of those look like. These are from Brittany Patterson's article. And I thought a good mix. These are both West Virginia. This is another abandoned well. And so one of the other challenges that we're seeing, and again, part of the reason I'm not talking about fixing the law, we're supposed to plug them. We have the laws on the books of how to do it, when to do it, and who should be doing it. Finding the people to do it, having the money to do it is an entirely different conversation. And that's the conversation that we need to change in how we think about what we're doing with these. So we see more challenges. 8,000 to 200,000 wells at a minimum need to be plugged in Pennsylvania, according to their recent study. They estimate, and I love estimates like this, it's going to cost us between $340 million and $8.4 billion. That's not really budgeting, but those are the numbers that, if those are the numbers we have to do, that's what we're looking at. So that runs to about $42,500 a well that they're looking at for plugging. The funding source, the primary funding source for that, by the way, is $150 for a new oil well or $250 for a gas permit. You can imagine why they're not tracking the funding that they might need to make this happen. But notice the other problem that we have here. We're using new wells to try and help us support and plugging old wells. And with the production that we're getting, the wellhead, as was mentioned in this region, we get more gas per well than any place in the country. I think Doddridge County has the highest pressure per well of anywhere in the world. And so to plug these old wells, of which we have thousands, it's $25,000 to $75,000, depending on where we look. And so we have to figure out a funding mechanism. Ohio has looked to do that, and this is a good example of how they did. HB 225 passed this year, and the bill said we're going to put $15 million of funding for plugging the wells for fiscal year 2019, which increased, I think, by $7 million, according to the article I was looking at. And that's basically saying, of the severance taxes coming in, we're going to take 30% of that money and put it into maintaining what we've been doing before, right? That's a lot different than $150 per well in Pennsylvania. That's saying we're going to take our severance taxes and use that. Again, another argument for severance taxes to be used for this process. And we've heard severance taxes, we want to use severance taxes in the legislature doesn't, but a lot of people have talked about using severance taxes for things like funding PEIA, supporting teachers, supporting DEP and supporting things like this. The magic of the severance tax that people seem to be forgetting is that if you want our gas, it's here. I grew up in Michigan. As we all know, when GM decides to shut a plant down, those jobs go somewhere else, or they don't make cars. But they can go somewhere else. Doesn't work that way with coal, doesn't work that way with gas, doesn't work that way with oil. It's here or it's not. You want it, come get it. And so it is a different economic conversation than when we talk about attracting or taxing new businesses. It's a fundamentally different conversation. And I think Ohio, incidentally, that bill started at 50% to plug those wells and track it down. The legislative process got it to 30%, but I think that's still a good example of using common sense and good priorities. We have a recency bias. We know that things that tend to be close to us are things that we tend to want to fix. Things that are old, we tend to want to ignore. This is a place we shouldn't be ignoring. We should be looking forward to what we can do to get these things that don't benefit us, that don't have upside, that really are simply problematic. And incidentally, it's not just greenhouse gas emissions. Those things are leaking gas or oil into the water and the land around them. It's not just greenhouse gas emissions that are the problem. History has a tendency to repeat, so we need to plan ahead for the wells that we're currently drilling. Right, these wells will need to be plugged one day, and we're going to need to deal with that. We can't continue, well, we can continue the cycle, but it's not healthy and it's not productive. We need to start changing some of that. We have thousands of new potential wells that at some point are going to need to be dealt with as well. And so finally, as I mentioned, this is about priorities. These are things that we can deal with. You can build it right into the cost of doing oil and gas operations. It comes out of the severance tax. It comes out of the price of doing it. It's a lot easier to observe that to enforce it. Right? It's not as easy to enforce. But if we prioritize dealing with our old wells while we plan with these new wells, there's a tremendous amount of opportunity. If we've got the laws to do it, we just need to fund it and make it happen. Easier said than done, but if we prioritize it, that's something we can do. Thanks.
So I think all of our panelists today have talked about Environmental Defense Fund, EDF, and all the great work that that organization is doing in the area of methane emissions. So I thought it appropriate that we actually have somebody from EDF here. This is Andrew Williams, the Director of Regulatory and Legislative Affairs for U.S. Climate and Energy for Environmental Defense Fund.
Thank you. See if I can open this file. There we go. Okay, there's a lot to cover today, right? And we haven't stood up in a while. Do we need to stand up, Tom? Stand up and stretch around. I know all of you in this room trying to get legal CLE credits are waiting for that break after I'm done. Oh, yep. Does it, Ken, is this the one that works?
Pointer. That pointer works.
This pointer.
That one's mine.
Okay, we're going to collect a few questions, I think, if you have any, up here at the front from the previous panelists. Okay, so let's wind it up and sit back down if you can. So first of all, thanks everyone for sticking around. You know, we all care a lot about oil and gas, the protections for communities around oil and gas, and the protection to our state's economies that is associated with oil and gas. My name is Andrew Williams. I work for the Environmental Defense Fund, and for those who may not know, EDF is an international climate-based organization really at our core. We focus on a wide variety of environmental issues and really seek out market-based solutions or practical solutions where those can be made to fit. One aspect of our work that doesn't come without its fair share of criticism, really, from both sides of the aisle. But we strive to collaborate with several, even here today in front of you speaking, where we can, and really only use confrontation or legal action where we have to. So, and I am going to talk to you a little bit about that legal action today for those attorneys in the room. But what I'm not going to do is go back through a whole bunch of the emissions data that you've just heard about. So my presentation, which I'm going to go through about half of it, the other half you guys are going to be sent. If you have any questions about any of our studies, I think Ken and Zach did a great job going through most of the results. So I'm not going to go through that again. So feel free to email me, call me. My phone number's up here. It's up here again later on. I'm happy to answer any questions. And you guys are free to, Tom, to send this slideshow around to whoever you may want. So Ken, is this the thing that moves the slides? There we go. Okay. So outside of methane, EDF focuses in several areas of oil and gas regulatory development. And this slide's not working for some reason. But those have a lot, we talk a lot about air emissions, right? We talk a lot about how you drill a well, so how you complete and then hydraulically fracture an oil and gas well. What I don't hear a lot about, at least at the state level, or definitely not at the regulatory level, is how do you manage community impacts? So how do you manage things like noise, truck and road traffic, construction of roads, generally. So that's a whole different side of EDF's work that's not associated with air emissions or even how you drill a well. So I just wanted to point that out. We're not solely focused as it relates to oil and gas on air emissions, which you're probably most familiar with. In addition to that, we probably spend as an organization an equal amount of time and definitely resources money-wise on things that are not oil and gas at all from an air standpoint. So our organizational goal is to, as a few panelists mentioned, get to as close to a zero carbon future, a lower carbon energy future as possible. And the first foray into that as it relates to climate on the ground at the state level, at least for EDF, was with methane emissions. Because we knew at the time we started this, roughly 25% of the global warming that you're experiencing today comes from methane, which Ken probably went through earlier. But what we didn't know, right, is what the heck was happening, where methane emissions were coming from, how big of a problem they were. And so I'm going to boil down the science part of this presentation into the one fact that now we do know, number one, that methane is a problem, right, and two, that emissions are drastically higher. Even if you go with the numbers Zach just presented earlier from Pennsylvania, the Northeast Pennsylvania study, emissions are, I would even argue, somewhere around 4 to 5 times higher than where EPA inventory has them current. So we know there's an issue. Now we at EDF and several others are on to sort of what are the solutions to the problems. And one of the ways that we have, worked to come up with those solutions is this collaboration. This is a rather hokey slide here, but collaboration. And it's important to note this, I think, for several in the room, because research, policy development, advocacy at the legislative level and at the regulatory level doesn't come from one organization, right? Just our research alone was a collaborative effort from over 100 scientists and 30 oil and gas and other, production or local distribution companies, et cetera. So working together where we can find those nexuses is one of the most important aspects, I think, of our work, not only today, but moving forward. So here is a domestic picture sort of the general areas that we heard about today. I wanted you guys to have this. In the slideshow presentation, there's a link to our website that has quite a bit of data on our different scientific studies that's associated with this graph. So when you get it, if you're clicking through it and you have any questions, don't forget, feel free to email me or call me. I'm happy to answer any questions, but this is an overall picture of sort of where the unconventional oil and gas production mainly happens in the U.S. Do what? Rogersville in Arkansas? Yeah. Yeah, sorry, that's the Marcellus is overlapped with the Rogersville Shale. Sorry, the whole area there actually includes the Rogersville. Yeah. that the only question? Sorry. Okay. So this is also, you saw this before, and I'm just going to explain the table and not go through all of the numbers here, but this gives you an idea of leakage rates per sector. So you saw the 2.3% leakage rate that Ken and Zach presented earlier, but this is broken down as the EDF studies sort of came in, the leakage rates per sector. So starting with the production, which is clearly the largest sector that Ken pointed out earlier, and all the way through to the local distribution side. And everywhere in this presentation, we compare the EDF methane synthesis work to 2017 EPA emissions numbers. And the main takeaway there, again, to reiterate what Ken said before, is that emissions are some 60% higher than what's currently reported by EPA as measured, site-level measurements through the methods that they described on the ground by actual scientists, some of them here at West Virginia. And I'm not going to go through the takeaways other than the last one because you've heard them all before. I will mention that the nomenclature associated with some of the terms that Ken and Zach talked about earlier has changed a little bit, at least from the advocacy and regulatory community. We used to talk about abnormal operating conditions or those events that make up most of the emissions but are very few in number as super emitters. We no longer talk about those, but you may be familiar with the term super emitter. We talk about them as abnormal operating conditions for the very point that Zach made earlier. We're trying to ascertain what the actual thing is that's happening, what's abnormal about the situation. And it may not actually be a super emitting part from an oil and gas facility. It may be, but it may also not be. So we are now talking about those events as abnormal operating conditions. But the biggest part, and what I want to focus on today, in large part, is the idea that regulatory action works. I always like to use the analogy of the federal New Source Performance Standards, or NSPS Quad OA. In between 2012 and 2014, there was a requirement that went into place at the federal level that controlled drilling well completions. So before this requirement was there, an operator could drill an oil and gas well, complete it or hydraulically fracture it, and whatever gas was there until the well was ready to be produced, they could just vent to the atmosphere. And that was roughly making up 60% or so of the emissions that we were seeing in the early years of our studies. That requirement went into place, first one in 2012, and immediately cut methane or leaked natural gas emissions by roughly 50 to 60%. So we know that when left to their own device, operators don't always make the most environmentally sound decisions, but when there is a regulatory floor set and requirements specific to operations placed on these activities, that they actually do work to reduce emissions, and that's just one area. The other one is leak detection and repair, which I'll talk about here in a second, but that's a requirement where you simply have someone show up on site to do a leak survey. Sounds a little crazy that it may not be happening to begin with, but just having someone show up on site, do a survey, see if there's anything leaking, and then fix that or schedule it to be fixed was also not happening in the oil and gas space on a frequent basis. So you heard Ken talk about, or Zach talk about on a quarterly basis for coal mine monitoring. That's just now, taking hold across the U.S. domestically at the state level, and it's estimated that could have some 70% emissions reductions from that specific emission source category. So we know regulations work, and I wanted to show you this video. I don't know if it's going to work. Oop, no. Does anyone know how to play the? Okay, well, you'll have the video. The video is a FLIR image, which is a forward-looking infrared camera footage. Leanne in the back. Leanne, you might stand up for folks. She works for Earthworks, and they have a large project nationwide that goes out using FLIR imaging infrared cameras to do assessments, site-level assessments of methane emissions, as well as other things. But it allows an operator who would not otherwise be able to see a leak of natural gas actually see natural gas leaking, and that video is in this slideshow, which is not playing. So either ask Leanne, and I'm sure she can show you on her phone, or email me, and I can definitely send you some other photos if you are interested in seeing that. And I apologize, the video doesn't work. So on a state level basis, what's happened, now since President Trump has taken office? In 2014, the Obama administration finalized methane regulations at the federal level. And currently, President Trump's EPA is in the process of sort of rolling some of those regulations back. And what we have engaged in at EDF, and a lot of folks that I see here in the room, familiar faces, I know at the state level here, even in West Virginia, have done, is sort of engage in what I would call a cooperative federalism approach to make sure that we have the most protective standards possible on the ground, protecting communities like here in West Virginia or across the borders in Pennsylvania or Ohio, as we can in the absence of, or potential absence of federal controls. So at the state level, we'll start the first state in the country that regulated methane emissions comprehensively, so from conventional and unconventional and new and existing sources. So those wells that are going to be drilled in the future are new, and those that are already existing are existing wells. So comprehensive regulation was Colorado. And then next we have California, which earlier this year regulated comprehensively methane emissions. And then Utah, Wyoming, and North Dakota. North Dakota is interesting because they don't actually regulate methane emissions, but they do regulate pretty significantly flaring emissions, which before they put those requirements in place in 2013, 2014, those emissions were also being vented. So it was like a completion of a well happening every day, 24 hours a day. So that's had a pretty significant impact on the emissions coming from North Dakota. While they're not specific to methane, they do control methane. And then interestingly enough, surrounding us here in the Marcellus region, the state of Ohio and the state of Pennsylvania are both moving forward to regulate new and existing sources of methane pollution within the oil and gas sector. There's an estimated around 40 to 50% reduction potential by comprehensively regulating methane in the area. Ohio just started their early stakeholder, what they call an early stakeholder process for generating comments around the proposal to regulate new and existing sources. In Pennsylvania, just 3 days ago actually released their draft existing source methane rule. The methane, and theirs is actually a methane and VOC rule. So we're seeing some pretty significant progress at the state level. One thing I would note to the comments earlier, while we're talking about the state level, is funding is a huge problem, right? We can do all the science we want to and fundraise and complete and synthesize as much research as possible. We can advocate at the legislative level for as much policy development as possible. But when you get to the funding side, right, that's where sort of sometimes it all falls apart. So in a state like Pennsylvania, I'm just going to give you a couple of examples. Here in West Virginia is funded a little bit differently, but in Pennsylvania, their oil and gas program is 100% funded by well permit applications. So there's no funding coming from the general fund of the state budget. And that's important because before this year, they were only receiving a few $1,000s for a well application, and they only just this year tried to up that to around $12,000. So there are some significant hurdles to get over. And I don't know whether, they're because of the polling statistics, just generally that you were presenting earlier, but it would be an interesting thought exercise to go through, sort of the political calculation that we are subjected to personally here in the Marcellus region that's different from the rest of the U.S. To sort of get at, some of that thought research. So those of political science, law students in the room, there's a project for you. I mean, EDF has funded a lot of this research. I'm not saying we're going to fund that research, but it would be interesting to see. And I mention it because specifically, again, before we leave the state side, when you think about orphaned and abandoned wells, that to me is a new sort of emerging issue within oil and gas and regulatory policy, right? It's definitely not a new issue for the oil and gas industry, but it's a new issue that we are starting to grapple with as advocates and legislators are starting to grapple with, and definitely regulators. And it's all around this idea of money, right? How do you deal with the liabilities associated with plugging a well? You've got both ends of the spectrum where here you saw only a few $100,000s are allocated for well plugging, but then you have a state like Texas where they've actually incentivized oil and gas companies to pay millions of dollars into a general well fund not associated with a severance tax or any sort of a production tax to actually plug those wells, right? So you would think a state like Texas, as conservative and oil and gas minded as that state's economy has been for years, would not be in that mindset, but they are, right? So I know that there is movement within the two polarities of the spectrum. And I will note that Ohio has a much higher severance tax rate than West Virginia, and Pennsylvania has no severance tax. They have an impact fee, but so there's a big disconnect, if only in that respect. And one other note on the state level side of things that was mentioned, and I just have to mention it. It's on the orphan and abandoned and legacy well issue. The numbers that are up here are, I think are pretty staggering, right? That you saw before relative to how many wells the state's going to have to deal with, whether it's 55,000 wells or it's over 100,000 wells in Pennsylvania, whatever the number ends up being. One of the issues that you should take away from today, knowing, right, is there are regulations on the book, right, in most every state that have oil and gas production relative to plugging. But one thing that does not get a lot of attention is the bonding requirements associated with drilling wells. So it's very low. Some of the bonding requirements to drill a well, you only have to put up a $25,000 bond. There are others that are higher or what have you. But if you can imagine, right, the numbers you heard before on the $47,000, that's a low number, dollar amount to plug a well. $25,000 doesn't even, it barely covers half of that. And that's the low end. And so you've got companies that realize that there is a incentive to buy up some of these orphaned, or not orphaned, but legacy low-producing wells, package them up, and then sell them, or just take the profit, from the purchase. And there's a big sort of movement going on right now within the series of combined state legislator groups and state regulator groups trying to figure out how to deal with that. Because if companies come in on the finance side and start buying up all of these low producing wells, at some time, if those companies can't make enough money and they all go bankrupt, then the numbers that you talked about here on the slide earlier are probably double. And that only just increases the financial risk to states like West Virginia and, every state that has oil and gas production. There's a specific company for the law students in the room, if you're interested in that topic. Diversified is the company that is purchasing right now these wells. It's an interesting topic you should look up and watch how the case law develops around that specific company. Yes.
So, well owners should be well aware of that and avoid it, because injection of frac waste
Yeah.
carries a whole host of problems.
Yeah, so I'll make a note and I will address that here in a second. Let me go to the federal side on the sort of, I was asked to provide the landscape on the legal aspects. I think that's super important, and let's go back to it here in about, 3 or 4 minutes. Okay, so I also threw this slide in here. There's no reason to read this right now. You'll have this and you can look at it. But this is a breakdown of our cost curve analysis that EDF commissioned with ICF in 2014 that shows the cost effectiveness of different control technologies. So the control technologies that are cost effective, the dynamics are shown here. It's too complicated to go through in today's presentation, but I'm happy to answer any questions that anyone may have, and I wanted you to have the information. This is, by example, this is also very similar to what the EPA used during the 2014 NSPS development. Okay, so speaking of the EPA, let's talk a little bit about the federal landscape. So in I mentioned before, 2012 to 2016, there were a couple of different revisions to the federal landscape as it relates to methane and oil and gas air emissions and their regulation at the federal level. Started with that well completion, new source performance standard in 2012, all the way up to 2016, when the site level new source performance standards were finalized at the EPA. So that's an important designation and differentiation, the EPA never took action to regulate existing facilities. It's one of the things I think, you know, is hard sometimes for regulators, not only to look prospectively on enforcement, but also to look prospectively or backwards. We don't do that very well, right? We sort of have a tendency to permit something, let it happen, and then not think about it again. So there's a need, a pretty big need, at least at the state level now, to do that, go back and look at the requirements for existing facilities. This is sort of the legal steps that the 2016 rule has gone through over the last year. The main takeaway from this slide is that the 2016 New Source Performance Standard, which is otherwise known as Quado A, is in effect, and the federal government is regulating methane emissions right now, but that's currently under not only litigation, but the threat of weakening. So there's a current proposal on the books to weaken the NSPS, you know, and essentially that is, at least as it relates to right now, the president issued an executive order essentially to have his agencies, not just the EPA, but his agencies go back and sort of look at all regulations that deal with oil and gas production, and then decide whether or not there needed to be an action or a revision made. And then he specifically noted that there needed to be attention paid to the Bureau of Land Management reduction of waste rule and the EPA Quado A NSPS, which dealt with methane. And so, you know, there's now a proposal on the books to reduce the frequency of leak detection and repair requirements, essentially for well sites and compressor stations. And the unfortunate part to this is that we estimate at EDF that while the current framework has the potential to reduce methane emissions by between 40 and 45%, if the current revisions and a couple expected revisions are allowed to take place, that could reduce the effectiveness of those federal policies and programs to only 3% reduction of methane emissions. And that's using the numbers that Ken presented earlier from our synthesis work. So I wanted to also mention that, you know, it's not only a regulatory process that we're looking at. There's also a large part of methane abatement and emissions cuts that can be made through voluntary efforts. Right now, there are 13 major companies, several of which actually operate here in West Virginia. Shell has historically been here. I'm not sure if they have production here now. But at least historically they have. They're one of the large companies, multinational companies that have a commitment to reduce methane emissions. Most of the commitments are around that 1% level that we heard about earlier. That was from a previous EDF study, and there are 8 companies that are involved in an organization called One Future that are all, they all have the goal to reduce their methane emissions down to that 1% level. And this is just a slide to sort of show you a snapshot of just one of our projects at EDF, which is the launch here of our methane monitoring challenge. And this is an idea of the type of folks that we partner with to develop, incentivize, and hopefully you know, bring onto the ground new technologies. Here it's specific to methane, but we also, you know, have other efforts and other programs at EDF, and you'll have this, so there's no reason to, you know, memorize it now. And then I also included here a quick link to all the studies you heard about today. So you'll have this as well. So that, I mean, I think that there's no reason to cover any more of the study work from EDF at least, and that's a general overview of where the regulations stand, or at least where I see them standing now. Just to address a couple questions. One question earlier was around the differentiation between conventional and unconventional production, not just here in West Virginia, but across the U.S. Most all conventional wells, which are the vertically drilled wells, are also hydraulically fractured. There's almost no well that's drilled, at least new well that's drilled, that does not need to be hydraulically fractured to allow it to produce oil and gas. So if you refer to, there's sort of a problem in nomenclature when we refer to conventional and unconventional as only being referencing the process of hydraulic fracturing. That's not quite correct. I think the better definition is to think of them as vertical and horizontal, because those horizontal wells are also hydraulically fractured, but normally several times across, along the process, so they have a higher production rate. But there are very similar concerns associated with both vertical or conventional as there are with horizontal or unconventional production across the U.S. Okay, so a quick answer to your question then or comment, I guess, to the question on companies coming in and buying older wells and using them for either a disposal well, or sometimes they'll also use older wells to flood an area with CO2 to increase oil or natural gas production. One of the areas that EDF has focused on is developing what we call a model regulatory framework, which has been deployed in states like Ohio and in large part here in West Virginia and in Pennsylvania. And that actually deals with well communication as one aspect, which is when maybe an old well may have been intersected by a new well, and so there's a potential for contamination to happen as it relates to the new production coming through the line and then hitting the old line. It could cause safety problems or health problems or really any problem associated with old wells. So there's a whole slew of environmental reasons why landowners should be hesitant or at least at the very least skeptical of a company coming in to buy an older well like that. I would recommend that you talk to an attorney before something like that is done so that there are appropriate safeguards are put in place before any sort of transaction like that happens. But do know that, early on when regulators and companies were able to say there are no impacts from hydraulic fracturing, in large part, we have found at least very little, while there's little data to show water impacts from hydraulic fracturing, there are some data points that indicate that well communication did result in some water contamination, whether it was surface or subsurface water contamination. So there are some significant issues associated with those issues, which sort of touch property law as well. That's why I would say you need to talk to an attorney as well. Yeah, so it's a great question. Any other questions? I'm happy, yep. Create regulation on methane, just generally? So that's a great question. There have been several ballot initiatives. I don't know of one specifically related to methane, but several related to local control. So the city level ability or county level ability to control where drilling happens. Most recently in Colorado, that ballot initiative failed. But that does happen. That also happened in North Dakota, probably when you were in North Dakota maybe, around several of these issues and proper planning and siting of wells. Okay, I will sit down and we'll take questions from the panel, I guess. Thank you very much.
So one of the questions is on the global warming potential. Basically the difference between CO2 and methane, 86 more times potent as a greenhouse gas than CO2 over a 20-year period and 28 times more potent over a 100-year period. One, can you confirm those numbers and explain the difference if these numbers are correct? But that whole notion of global warming potential of methane versus CO2.
Talk loud. So the question is, are those numbers correct? I believe those numbers were the correct numbers. And what is it referring to? It's actually, interestingly, Zach recently corrected me. I always thought that was by molecule. It's per unit mass of the gases. And the difference is caused by the fact that the absorption bands for methane are in areas of the atmospheric spectrum that are not already saturated. So there's a lot of CO2 out there. So all the CO2 absorption bands have almost absorbed all the infrared radiation that they can. As you add more CO2, it's actually on the edges where you get some called pressure broadening, that you get a little bit more absorption. It increases more like a logarithm of the number of molecules. But for methane, the bands are not saturated. So you add another molecule, it absorbs more infrared right away. And so the methane is a more potent absorber because of the location in the spectrum of the infrared radiation absorption. And the time scale is related to the lifetime in the atmosphere of the methane. Methane hangs around about 10 years before it gets oxidized and eventually turns into CO2. But CO2 cycles between the biosphere and the atmosphere for a very long time, eventually only being stored by the oceans. The ocean has one sink time scale that's about 300 years, another time scale more like 10,000 years. So the average lifetime of a CO2 molecule is thousands of years, to be honest. So it's a complicated accounting. If you went for a 1,000-year global warming potential, they'd be about equal because the methane turns into CO2.
Do we know anything about the emissions outlook associated with the Shell cracker plant in southwestern PA and the proposed ethane storage hub? Anything?
It doesn't exist yet.
But projections or anything, estimates?
I think the projections are actually public through the permitting process in Pennsylvania. But those are emissions factor driven. I don't know if these are on. So the estimates for the cracker plant in Pennsylvania and also for any plant that is proposed, go through the regulatory body. And I know in Pennsylvania, at least, the projections are public. But those are never good. Those are not going to be actual because that plant is actually not even constructed.
We are trying to get some seed funding to start to make measurements before the plant shows up.
Related question, given the amount of dollars being spent on pipelines and cracker plants, how likely is it that we will only use natural gas for a short term? The bridge to nowhere, maybe? I don't know. Go ahead.
We're going to use it for a while, probably. Ken's not going to like that answer, and I don't like that answer. And this may be a more pessimistic view, but honestly, the switchovers I've seen tend to occur when it's economically beneficial to switch from one to another. So as long as natural gas is beneficial to someone, someone's going to be using this natural gas. So it's going to be a long-term problem. It's a really weird conversation I have to have in that, yeah, you should totally switch over from coal to natural gas in this area right now, but 20 years from now, I'm going to be coming back at you and saying, this is bad, we need to switch away. And it's a confusing message. It throws people off, and I know 20 years down the road when I'm 40, whatever, people are going to come back to me and say, you said this was good, you said we should do this. So yeah, it's going to be a problem, and there's really probably no obvious answer to how to make it just short-term and not a long-term source.
I have a slightly different take. I agree with Zach on the general premise. Although I think we got to think about this from a holistic standpoint, right? It's sort of the projection I gave of EDF as an organization, right? We can't only focus on oil and gas. We've got to focus on the holistic view of sort of how we're incentivizing energy production to happen across the U.S. and internationally moving forward. The important point I think we should make on this question is, even if we went to 100% renewable power tomorrow, right? In the power sector, we'd still be here talking about the impacts of natural gas because really only a third of the natural gas produced today is even used at the power plant level. The other 2/3 are used for things like heating and cooling your house and industrial processes, right? So the power sector is only one part of the conversation if we are having a conversation about whether or not oil and gas or fossil fuels generally are going to remain as part of the energy mix moving forward. And that's a big focus at EDF, and I know, I don't know who else works within the environmental space here in the room, but a big push of ours is to develop, regulatory metrics and legislative metrics, political metrics for how you incentivize those changeovers, the sort of finance mechanisms, the actual energy markets managed here in this region by a company called PJM, right, are naturally sort of decarbonizing. The coal plants are sort of naturally retiring because they're not as cost effective anymore. That will hit a point at some time where the markets will the equilibrium will be met, and new political incentives will have to be put in place, in my mind, around incentivizing the lower cost, lower emissions sources like wind and solar. So I think it's a dynamic answer based in science, but not solely based in the science on this one.
I guess one more time scale that didn't get mentioned, and I don't know it very well. I don't know if we do know it very well. It's just if we have a petroleum and natural gas engineer in the room, how long does one of these wells continue to produce? Eventually, these wells that we drill will stop being productive, and there's a finite time to that.
I think the production cycle is about 6 to 7 years. You're down to about 10%.
So that's not that long.
Horizontal.
That's not that long.
Yeah, but the difference with this is that with these processes, they'll drill more wells on that well pad. And so it's just a different model than what we've seen in conventional wells that produce longer. And so the particular well won't last, but their ability to put new wells, and they're going farther. I mean, when we started looking at horizontal drilling, you were looking at a 3,000-foot lateral was remarkable. Now they're doubling that for a third of the cost and going longer. And so the technology is changing. And I think that's one of the things that plays into this question about how long for natural gas. I think the industrial processes part, there's not a clear change. There's not even a change on the horizon for a lot of those parts. But on the power generation side, home heating, there are some opportunities, and they are, I think, scientific to some degree. They're both technology and cost. I mean, when I moved here in 2012, a number of the utilities said there is no way I can live without coal plants. At least one of those major utilities saying, I'm good with gas and renewables. That's a change for one reason. It's because gas is cheap. And so as we start phasing out some of the older plants and start phasing in new ones, gas plants come online, as the price goes up for gas, for example, wind and solar are getting more and more competitive, and there's other technologies that we might be able to see that can move on. And so I think part of the incentives, I think it's right, but some of that is to continue research in a variety of different ways, because there are technological answers to some of these things if we have the political will to support those.
Absolutely.
Sure.
When you were talking about the difference between federal and state, what was taking place, it shows you how little I know about this stuff still. I sort of had the impression that federal regulations, that there was at least a set of federal regulations that involved drilling on federal lands, Bureau of Land Management, as opposed to non-federal lands. These regulations that you're talking about, the federal ones that are on hold or being litigated against, are those regulations that apply across the board to all wells?
All new wells.
Pardon me?
All new wells.
All new wells.
Yeah, there are
So
two.
the federal government is able to exercise jurisdiction over all new gas wells.
Right. Under the
They don't
clean.
have a jurisdictional problem.
Yeah, under the Clean Air Act, we're talking about air emissions.
Yeah.
So under the Clean Air Act, yes, they can regulate all sources of criteria pollutant.
Separate regulations for drilling on federal lands?
There are, and that's the Bureau of Land Management rule that I was referring to.
That's not what you were really.
There are two, yeah, I did. The Bureau of Land Management is one whole sector of the regulation at the federal level, and then the EPA rule that applies to all new sources is the other one.
And there's litigation related to those regulations too?
Both of them, yeah.
Both of them?
Yep. No, that's a great question.
Josh, you may have covered this question. What role do orphan wells, abandoned wells where the operating company cannot be found or has forfeited their bond, play in methane emissions?
Yeah, I mean, it's a huge issue. And we don't know, without going from well to well, how much each well is leaking. I mean, I think that's part of the challenge. And so we have estimates, and we get a variety from the studies find, even from abandoned well to abandoned well, they find wildly different emission rates. And so it's a huge part of the problem. One of the things to note, I think, on those become generally a problem with the state. I mean, the landowner, if it's found on their land, they often can't afford it and are certainly not going to be incentivized to do anything about it. The other thing on the bonding requirement that I think is worth mentioning, a number of states have bonding requirements that they make the company pay a particular bond, so it might be $250,000 regardless of how many wells they drill, which is absurd. And so that is a particularly problematic part of it. I mean, if you don't link it to the well, you don't have any recourse. And so some of the big companies say, don't worry about it, we're so big. And then, as Andrew mentioned, some of them are selling off some of those wells, so that becomes a potential problem. And as we all know, energy companies are not too big to fail.
What we've seen in the atmospheric data is that you do not see much of a signature from where you would expect abandoned wells to be in terms of methane emissions in Pennsylvania. Our best guess is it's not really a huge methane source, but the Pennsylvania DEP is very concerned about them more as a health hazard. I mean, there are these holes in the ground with gas in them, and people don't know where they are. And you go and take your tractor out and you run into an abandoned well, that can be a disaster. And so our best understanding is it's not as big a problem as a methane source, though taking it out would be fine, as it is a health hazard.
I would caution on that from what we know.
We don't have.
Limited experience that we've had, we can go out in Mon County and find a well that has never produced anything that is emitting more than one of these compressors do. So we just don't have an idea, really.
Well, we do have some idea, because we fly all across the eastern U.S., and we've never seen the plume from the zillion abandoned wells in northwestern Pennsylvania. So they don't add up to a big unified source, at least, because we would see it in the atmosphere. That's one of the great things about the atmospheric data, is if there's a big source out there, it's going to show up. It could be a little distributed source all over the place that doesn't make a plume. That's possible.
I guess I was referring to the ratio. There's no production, right?
Oh, yeah,
It's
definitely.
normalized
Yeah, absolutely. They're no good for energy production, that's for sure.
Okay,
Princeton University, we came and did a gas emission study in New Jersey, Pennsylvania, West
Yes.
Virginia, and they said West Virginia was the worst they've ever seen.
this just in. There's a lot of gloom and doom in climate news. Where do you draw hope, and where do you realistically stand on the hope to deep despair spectrum? Somebody should get an award for this question. But
What was
any thoughts?
the question is, where do we stand on the
Hope to deep despair spectrum.
I'm moderately hopeful. That's an easy answer. Not excessively hopeful, though. Who asked?
I'm a big believer that the economy and whatever's economically beneficial to the most people is going to be what ends up driving the solutions most of all. We can mitigate what's going on right now to the best that we can, but in the end, any switch over to renewable energy, in my opinion, just relies on being economically advantageous. I would switch my house over to renewable energy right now if it didn't cost half of my house payment in order to do it. So if that stuff became cheap, if renewable energy just continues to become cheaper, and it will, you're going to see that switch over occur faster and faster. So to me, that is the driving force. And it's hard to know whether to be optimistic or pessimistic about that, because it's really hard to predict new technology. 10 years ago, if someone had told everyone we'd be converting to natural gas in Pennsylvania from coal, they would have looked at you and been like, what? But suddenly we now have all of this natural gas in this area. So it's not always easy to predict what energy is going to look like 10, 20, 30 years down the road. So I'm kind of like, I don't know.
It's not that expensive.
One other thought on that, too. That's interesting, and I agree with it. The thing that I think is interesting on the political spectrum is during a time when normally companies and, big economic drivers, at least in the U.S., fall behind, the politics, in our case, the current federal politics, I actually see a whole bunch of multinational and domestic companies making pretty solid commitments on climate initiatives, using the word climate, making commitments to reduce their emissions. So it's not all, in my mind, around, around the company aspect of it, but I think that's an interesting dynamic as an environmental activist that in some ways wasn't even present during during the previous Democrat administration at the federal level. So while I agree it's an economic play, although I think the economics are actually moving towards our favor, at least from a carbon emissions standpoint, I do think the politics right now, the world we're living in today is an interesting one. As well, from the standpoint of how companies are reacting to some of the things that we've been talking about, specifically the regulatory rollbacks and companies coming out in favor or making further commitments to continue those practices, which just doesn't happen a lot.
Does one say it's always darkest right before the dawn?
It's also darkest right before night.
He's the young
goes
guy.
both
What's
ways.
going on here? I'm the old guy and I'm optimistic.
Couple more questions. What? Couple more questions. A question on mine openings with respect to, do they contribute to emissions? Is there a difference between emissions associated with deep mining versus surface mining? So the issues of emissions related to coal mining.
So surface mining, just taking the EPA's numbers themselves, surface mining pretty much has very little methane emissions associated with it. It's the underground mining where you get all of these methane emissions. So yeah, if you look at a coal mine in Wyoming, the state of Wyoming versus a coal mine in West Virginia, you have significantly different contributions to greenhouse gases because the Wyoming coal mines really have no methane associated with them. You're still going to have the CO2 though, and so it's going to be hard to offset that. Then you're going to have to look at the natural gas leakage rate to determine if one's better than the other there. But surface mining is definitely much better in terms of methane emissions.
You know, there's one other thing to note about that too, Zach, that you mentioned in Wyoming is important to note relative to the Pennsylvania study that these guys talked about before that showed such a lower emissions rate when compared to other basins across the U.S. for methane. Very similar to the coal mines in the West, the oil and gas wells in the East are drier. There's not as much liquids production, natural gas liquids production with the natural gas wells. Which means there's a lot fewer storage. There are a lot fewer storage tanks. And if you remember from my slide before, storage tanks and those abnormal operating conditions, storage tanks are one of the largest sources that make up those abnormal operating conditions in large part. So when you have fewer storage tanks, you're naturally going to have fewer emissions in a state like Pennsylvania or even here in West Virginia. So even the oil and gas wells are different as the comparison was just made to coal. Geographically.
One more question, Jim?
Yeah, at least three of you have mentioned the economics of natural gas versus renewables, and I just have to interject and see if anybody wants to comment on carbon pricing as far as a stimulant for renewables versus natural gas use.
So I think that's the answer, not necessarily carbon pricing, but limiting carbon, setting a hard declining limit on carbon. Is where EDF's policy is headed, which would then incentivize the development of a financial market to meet those limits, which is a scenario and a framework that does not actually pick winners and losers. You don't have to incentivize oil and gas over coal. You don't have to incentivize nuclear energy over wind power. The market does that for you on a cost basis and an efficiency basis if you're talking about a carbon market. So that's exactly where we need to be talking. But the way we're looking at it is not as much as a carbon fee as a declining limit on carbon. In theory, they could operate the same way, but other drivers make it such that if you can set a hard limit on carbon, you can ensure the outcome that actually carbon is going to be reduced from a policy. If you just simply place a dollar amount on carbon, I'm not sure that you can ensure the outcome.
Anybody else want to comment on that? Josh?
I was just going to say, I mean, I think a lot of economists look at it and say a carbon tax itself would be more efficient, but I think we've also seen that there's a lack of political will, at least in the United States, to go about it that way, whereas we've seen very effective cap and trade programs. I mean, the NOx and SOx, and it was wildly effective, and it incentivized people to do things that they wouldn't have otherwise done. And so, I mean, we have a carbon tax if you consider your 20 cents or 40 cents or 60 cents or 80 cents, depending on where you are, per gallon of gas. It could be a carbon tax, but are people going to tolerate a $2 a gallon tax? They say, no, we're not Europe. So I think there's a political possibility, but I have to agree that I think the carbon tax is both, at least in our structure and for these kinds of regulations have proven to be effective, and I think that's probably where I would push in terms of the effectiveness, because I think the willingness to be harder on the carbon cap is going to be better than a high carbon fee.
And so I totally agree with that. One other note, on the aspect of the role of oil and gas and other sources in that sort of a framework, there was a federal program that placed a cap on carbon during the Obama administration. It was called the Clean Power Plan, or the CPP, which has now been, or is under litigation as well, Tom, and revision and probably rescission. But there's a lot of modeling that shows, I'll use Pennsylvania, for example, that even coal out 30 years or whatever is still around 20% of the generation mix. Natural gas has a huge share of the generation mix, but you are seeing renewables priced into the market. And nuclear energy is interesting, but there's a significant body of economic modeling and emissions modeling around that specific Clean Power Plan originally, and now state-specific carbon actions. And there is a carbon market established in the state of California. There's a regional greenhouse gas initiative, which is otherwise known as RGGI, which is for most of the states in the Northeast and hopefully soon to be Virginia. So there are already examples and frameworks to build on. I don't know if you have any.
That's a good preview. Our last panel today is going to talk about putting a price on carbon. Let's give a nice round of applause to this panel. We're going to take a 15-minute break. I'll be back at 3:45 for a panel on solar with Autumn Long and Evan Hansen.